Okay, so I've set up a couple mole, stoichiometry, different volume, a lot of dimensional analysis problems here. And we're starting off a little goofy, and that's okay. We gotta keep interested. We're doing a lot of math. So in the anime about superheroes, character Momo uses her quirk or superpower to make a titanium staff with a volume of 848.2 centimeters cubed. I'm going to assume that's a solid staff. It's not hollow. And we're given the density of titanium, which is 4.506 grams per centimeters cubed, to determine the following. First, what mass of titanium is produced. So we simply start with 848.2 centimeters cubed. I always draw a line when I'm doing my dimensional analysis. If you prefer to write it out like this, do what feels more comfortable. This line and the vertical line, meaning multiplication, really helps me keep track of what I'm doing. But if it doesn't help you, don't use it. And then our density conversion is 4.506 grams. Oops, see, I did a mistake. I wrote it on the wrong part. And I immediately realized that because it wouldn't have canceled out. And that's part of how it helps me keep track. So we're going to write 1 centimeter cubed here on the bottom, because there is an implied 1 in this denominator, and 4.506 grams. And then I can see that my units cancel, and we can calculate that if I just punch this in, 848.2 times 4.506 is a lot of grams. It's 3,822 grams titanium. And I'm just going to 3,822 grams titanium. Set that there so we remember it. And then we can use this space to figure out how many moles that is. So I'm going to do the same thing. I'm going to set up our known quantity that we want to convert, grams of titanium. Draw a line, draw my vertical line, and then you could look this up in your periodic table, but in this case, since we're just dealing with one element, I have set it here. So 47.867 grams of titanium per 1 mole of titanium is the atomic mass of titanium. I've read it off here. And we're going to do the same thing. Cross out grams titanium, cancels out grams titanium. Equals, I actually have to punch this in, 3,822 divided by 47.67. I get 79.85 moles. So that's my unit left on top of titanium. And that has 4 significant digits. I'm going to try to keep significant digits in line throughout most of this, but no promises. So the next problem is about the international prototype of the kilogram. So the international prototype of the kilogram was what we used to define how much is a kilogram for over 100 years. And we don't use it anymore because it had problems. It would occasionally absorb molecules from the air, or it would degrade even though it was kept under 2 bell jars like you see in the background here. And it's made out of an alloy called PT10IR. The Alloy it just means an alloy is a mixture of metals, and this naming PT10IR is meant to indicate that it is 90% platinum and 10% iridium. PT10IR is not like a traditional way of naming compounds, and alloys aren't really named the way we named compounds in class, so just let it go. This is what people call it. So our questions are how many moles of platinum are in the IPK and how many moles of iridium are in the IPK. We should assume that the kilogram weighs a kilogram. It's kind of the whole idea, or because it's going to be easier to work with, 1,000 grams. So let's start with platinum. So I know that the IPK kilogram prototype is 1,000 grams of matter, and that only 90% of that is platinum. So I'm going to multiply 1,000 grams times 0.9, get 900 grams. And then I'm going to write down my favorite line and look at my periodic table to look at platinum, which has a Z number of 78, right? Z is the atomic number, and the atomic number is 78, but a mass of 195.1 grams per 1 mole equals, cross out grams of platinum, 900 divided by 195.1 is 4.6 moles of platinum. Okay, and now we can move on to iridium. So we could either subtract how much platinum we have. So, we could say we know there are 1,000 grams in the kilogram, and we already know that 900 of those are platinum. We could say the other 100 must be iridium, which would be correct, or we could do 1,000 times 0.1, grams times 0.1 or 10% and get to the same answer. So 100 grams iridium. And then I have to look at my periodic table. Iridium is right next door to platinum. It has a Z number of 77. So it's actually pretty similar in ballpark range of atomic mass, but we have an atomic mass of 192.2 grams of iridium per 1 mole iridium. Cross it out, cross it out. I don't have an on-screen calculator, but I get 0.52 mole iridium. And then the second part of this problem will also be about the IPK, just for fun. So the thing about the IPK is it got retired partially because it's hard to keep one piece of metal the exact same weight down to all the significant figures you need. The other thing was that we had to have replicas of it everywhere. So even though there was one definition of the kilogram, everybody had an extra one in case of emergency, you know, in case there was like a heist of the kilogram definition. So what this is asking is there's a replica in the United States. The IPK is in Europe. And there was a replica in the United States that lost 41 micrograms of mass compared to the IPK. Assuming all of the mass loss was metal, right? And that doesn't include any of the air that had absorbed onto the IPK, calculate the following. How many platinum atoms of the K4 went missing and how many iridium atoms went missing? So first we have to figure out how much of this loss belongs to each metal? I'm going to assume here that it's micrograms. This is a mu. This is the Greek letter mu. That the rate of loss of each metal was the same, right? And it wasn't preferential to one or the other element. So we know from our previous problem that the IPK is 90% platinum. So 90% platinum and 10% iridium, 10%. And you could write that as 41 micrograms times 0.9, and then 41 micrograms times 0.1. And I get that 36.9 micrograms that went missing from the K4 were platinum, and 4.1 micrograms that went missing from K4 were iridium. And then it's just another mole problem, right? So let's start with platinum, and 36.9 micrograms platinum. I'm going to draw my line and draw my other line. So there are two ways to do this. You can do this by remembering what your powers of 10 are to convert micro straight to grams. Another way you can do it in a way that I'm really comfy doing is remembering how many of each unit goes into each unit. So if that doesn't make sense, you'll see. So I know that 1,000 micrograms is the same as 1 milligram. And then I know 1,000 milligrams is the same as 1 gram. And then I'm back in business, right? I don't have to remember this 10 to the 6th power thing. I just let this all come out for me. And to me, this is a little bit easier to remember. If you like to do it between the powers of 10, do it that way. And then I just remember that 195.084 grams of platinum is the same as 1 mole of platinum. Now I'm in moles, so we have to use good old Avogadro. So 1 mole of platinum is 6.02 times 10 to the 23 atoms. And then I'm going to go, just as a check for myself, through my ladder and cross out micrograms platinum, micrograms, milligrams, milligrams, grams, grams, moles, moles. I'm at atoms, so I'm where I want to be. And to do this math, you probably want a scientific calculator. This comes out as 1.14 times 10 to the 17 atoms. So it's less than a mole, so that's another check, right? I'm in the right direction, and I feel good about that. So I'm going to write that down for reference. And then we can do the iridium problem. I'll choose different color for iridium. Okay, so it's going to be the same process with iridium, just slightly different numbers. But it's good practice. So we decided that 10% of 41 micrograms is 4.1 micrograms of iridium mysteriously went missing. And again, I remember that there are 1,000 micrograms in 1 milligram, or instead of going from micrograms to milligram to milligram to gram, you can do it the other way. 1 times 10 to the 6 micrograms is 1 gram, if this is easier to remember. And then we're back to our periodic table. 1.952.2 217 grams of iridium is 1 mole of iridium. And Avogadro's number is the same for everyone, so I don't have to look up anything. 1 mole iridium, 6.02 times 10 to the 23 atoms iridium. And our ladder is a little bit shorter because we directly converted from grams to micrograms, but it's the same process. So micrograms, micrograms, grams, grams, moles, moles. We're back in atoms. And when I punched this into my calculator earlier, I ended up with 1.28 times 10 to the 16 atoms of iridium. So a lot of atoms, and enough went missing that we had to change how we defined the kilogram, and we can't just all use different blocks of metal that we keep around the world. Oops, I meant to clear all drawings. Okay. So this problem I wrote because I Googled something on September 17th, and I noticed that the Google Doodle had some like pretty sweet chemistry going on. So I looked it up, and it is about Michio Sugimura, and she was a biochemist and agricultural scientist, but she's most famous for having discovered that there was vitamin C, oops, I didn't mean to cross it out, vitamin C in green tea. So she figured that out in 1924. And in 2021, you pick up a bottle of Oi Ocha brand green tea, and it says it contains 143 milligrams of vitamin C. Given the formula for vitamin C, determine the following. First, we have to determine the molar mass of vitamin C. We can't even determine the number of moles without knowing the molar mass, right? So to do that, I'm going to start making a little bookkeeping inventory for myself. Carbons, hydrogens, oxygens. So I have 6 carbons. I have 8 hydrogens. I have 6 oxygens. 6 times the atomic mass of carbon. So I have to look it up on my periodic table, but carbon is one we look up the most, 12.01 grams per mole. Hydrogen, we are using 1.008 grams. And for oxygen, we are using 96. Oops, I jumped ahead, didn't I? For oxygen, we are using 16. I keep writing this down wrong. 16 grams per mole, and you can double check on your own periodic table that that is what the atomic masses are. So 6 times 12.01 is 72.06, and this 8 times 1-ish comes out to 8.064, and 6 times 16 is 96.00. And then you can add all this up to get 176.124. And that's a lot of sig figs for what we're looking at here, but we're just going to hold it like this because these are known facts, right? We didn't measure these ourselves. There's not uncertainty in that measurement. And these are super well-known facts. And if you hear something in the background, it's my cat meowing against the wall. So I'm just going to write down 176.124 grams per mole here for our reference, and then clear up some space to figure out how many moles that is in our bottle. So in our single bottle of T, I'm gonna draw my line, 143 milligrams. I'm just gonna write vit C. And then I know that 1,000 milligrams is 1 gram, right? And I know that 176.124 grams of vitamin C, vit C, make up 1 mole vit C. And I know that because I just did it. So we can go through and cross out. You don't have to go from front to end. You can go this way, say grams, grams, milligrams, milligrams, and then multiply everything on the top, multiply everything on the bottom, divide what's on the top by what's on the bottom. So if I do that, I get 143 times 1 times 1, right? 143 over 1,000 times 176.124, which is large. It's 176.124 equals negative 143 to 176. 124. And I get point off my calculator, right? So I have to convert it to scientific notation. I get 0.00081 2. So I go into scientific notation, -1, -2, -3, -4, and I get, I'm sorry, right on top of the Google Doodle, 8.12 times 10 to the -4, because we went this direction, moles vit C. Okay, so then I saw that we were doing cool science Google Doodles, so I started looking at more Google Doodles, of course. And I saw that there is an older Google Doodle from 2014 that featured Dr. Percy Julian made a lot of advances in producing human hormones, such as testosterone, progesterone, which helps make us, able to provide people with hormone treatments. Because prior to his work, you had to go through just like a lot more effort to make as much of these treatments. So, excuse me. A friend of yours has a blood test done and his testosterone level is 500 nanograms per deciliter. That's a perfectly normal testosterone level to have. And given that the molar mass of testosterone is about 288 grams per mole, determine the following and know that the human body contains about 5 liters of blood. So what is the molarity of testosterone in your friend's blood? Treat blood as a solvent here, even though it is a complex mixture, but we're going to treat it as our solvent. And then how many moles of testosterone are in your friend's body? So let's get started here. 500 nanograms per deciliter, right? So here you can see that dimensional analysis helps you change multiple units at once. 1 liter, there are 10 deciliters in 1 liter. And then instead of going from nanograms to micrograms to milligrams, I'm going to actually just skip that and go from nanograms to grams. So I know that there are 1 billion nanograms per 1 gram. And I know that there are 288.413 grams of testosterone per 1 mole of testosterone. And actually what I should have done is written this, oh, no, never mind. I thought I would write this in reverse, but this is actually easier. So here we want the molarity, right? But we don't need to worry about knowing that there are 5 liters of blood, right? Because we already know what his total level was. So we go through and cross out everything that cancels out. So nanograms, nanograms, grams, grams, and we're left with moles per liter, which is the definition of molarity. So we know we're good to go. And I'm actually going to just write this up here for the sake of space. And I did this problem earlier, and I got 1.73 times 10 to the negative 8. If there is a mistake, it's usually in how you type things into the calculator, as long as all your conversion factors are right. And that's why it's important to write all this down, so you can go back and double check. So that's already in moles per liter, so it's molarity. And then we can clear up a little bit of space to figure out how many moles of testosterone that is in general. So I told you that there were 5 liters of blood in the body, and we're looking for total testosterone in your friend's body, assuming that all that testosterone is in his blood and not in any other places. So 1.73 times 10 to the negative 8 moles per liter, right? And then 5 liters. So you're just multiplying this by 5. These cancel out. I get 8.67 times 10 to the negative 8 moles. And one thing that actually makes sense to me here, and maybe this will help you keep track, I don't know, is that I'm actually on the same order of magnitude, right? And had negative 8 down here and negative 8 up here. And that makes sense to me because 5 is not enough to change an order of magnitude, right? It's a pretty small number. So being on the same order of magnitude makes sense. So I feel good about that. And then I think what will be the last problem in this video is going to be the next one. So we're just going to end on a goofy note. And I think that's okay. Oh no, your friend, you know, the one from the previous problem. Give me a second. Okay. I realized I had not made a calculator available for myself for this problem. So I had to pause it. Oh, we're back. So, oh no, your friend is attacked by a vampire. He survives though. The vampire only is feeling a little bit peckish and only drinks 555 milliliters of your friend's blood. That's about the average volume of a blood donation. Remember that your friend has a testosterone level of 500 nanograms per deciliter. If the vampire started with 4.7 liters of blood and started with a starting concentration of 345 nanograms per deciliter. What is the blood testosterone level? And this is actually going to be in nanograms per deciliter. I should have said that, nanograms per deciliter of the vampire after he finishes drinking your friend's blood. So this is sort of like another weighted average problem. So 4.7 liters plus 555 milliliters is 0.555 milliliters is 5.255 liters. Okay, so this is our total. So 4.7 liters over 5.255 liters is 0.894 or 89.4% of the blood now in the vampire originally belonged to the vampire. Sorry, vampire. And then your friend, this much of his blood, 0.555 liters, is currently in a vampire. So about 10%, 0.106 belonged to your friend. And then we can do a weighted average. And it's similar to how you might figure out your grade if you knew what your total score on each exam was, for example, and what the weight of each exam was, if they weren't weighted equally, or how you would figure out isotopes with a weighted average. So 0.94, that's our vampire's contribution. 0.894, so about 90% at 345 nanograms per deciliter. Plus, because we're mixing two solutions together, right? 106.106 times 500 nanograms per deciliter. And when I punch all that out, I get 361.4 nanograms. So we can see that the concentration of testosterone has raised a little bit, but not a lot, because most of the blood in the vampire originally belongs to the vampire. And then we can figure out what is the molarity. We just do the same thing we did before. So we've now figured that out. We have 361.4 nanograms per deciliter, 10 deciliters, 1 liter. And our big conversion factor for nanograms, 1 times 10 to the 9th nanograms, 1 gram. We're all in testosterone. It's the only compound here, so I'm not writing testosterone. 288.431 grams, 1 mole. And then we can check to make sure that what we'll get at the end comes out as molarity. So deciliters are out, nanograms are out, grams are out. We're getting moles per liter. I'm not crossing out mole. I'm affirming that the mole is the unit on top and that liter is on the bottom. And I get 1.25 times 10 to the negative 8. I did not do a good job of keeping track of sig figs in here, but this is a measurement we have, and we can say that this was 4.7 liters. So now everything is 3 sig figs. I can do that because I wrote the problem. If you didn't write the problem. So that's mixing solutions, figuring out molarity, and doing a weighted average. So that's the end of this section.